Greetings to everyone. I'm Kodishwari, Assistant Professor in AC Department at Punge Engineering College. And today we are going to discuss about an important microwave components which is known as the E-plane T. This topic is coming under the subject of microwave and optical communication. And we all know that these waveguides components which are essential for high frequency signal transmissions. So understanding this device is crucial because it plays a key role in power division and the signal combining in RF and microwave systems. So let us discuss about this component in a basic way. Before going into the E-plane T, first let us understand what the T-junction is. A T-junction is a three-port network, meaning that as shown in the figure, it will have the three terminals or three ports. So here the main waveguide, which is in this, which is here, is called as the collinear arm or primary arm. The additional branch connected with this main waveguides is called as the side arm or auxiliary. So depending on how the side arm is connected with the main arm, once again I repeat, depending on how this port 3 is connected with this main arm, we can divide these T junctions into two ways. Well, the first type is called as the E-plane T. When the side arm is connected parallel with the electric field of the main waveguide, it is called as the E-plane T. And when the side arm is connected with the parallel with the magnitude of the main waveguide, it is called as the H-plane T. So based on how we are connecting the side arm with the main arm, we can classify the T junctions into two types. One is E-plane T and another one is H-plane T. And the name T junctions is arises from this. If you are looking to the figure, either E-plane T or H-plane T, it is looking like an English alphabetic T. That's why these are commonly called as the T junctions. And today our focus will be only on the E-plane T. So, let us recall the properties of S matrix before going to the E-plane T, which will be helpful further. So normally this scattering matrix relates the incident wave and the reflected wave, by using which we will calculate the total power of the device and the characteristics of the device. Here Sij represents one of the component in the S matrix. Here J represents the input and I represents the output. For example, if I am using the letter S21 here, 1 represents the output and 2 represents the input port. Means that I am giving the input in port 1 and I am getting the output in port 2. Now let us see this diagram. If you look into this diagram, it is a two-port network. The port 1 is having the impedance of Z0 and the port 2 is also having the impedance of Z0. So from this figure we can understand that the port 1 and port 2 are perfectly matched with each other. So if so, these type of networks are called as the matched port. For matched port, the value of Sii will be equal to 0. Means that, for example, let me consider the input wave A1. In the matched network, when you are passing the wave A1, the total wave will be transmitted to port 2 because both impedance are matched with each other, so that from the output side we will not have any reflection. So all the waves whatever we are transmitting through A1 in the port 1 will be received in the port 2. So that is represented by using the term S21 here. We are sending the input in port 1 and getting the output in port 2. All the waves will be transmitted without any reflection in the input port, so that the S11 will become 0. So likewise, in the another port side also. When you are sending the wave from port 2 to port 1, there will not be no reflection because of matched impedance. So the S22 will become 0 when the port 1 and port 2 are matched with each other. And the second thing what we have to consider in the scattering matrix is the reciprocal characteristics. So reciprocal characteristics means that whenever we are passing the signal from port 1 to port 2, whatever the, for example, let me take in the port 1 we are having the 10 decibel signal, for example, let me consider that, and while you are transmitting that there is some attenuation loss, and in the port 2 you are receiving the signal which is having the value of 9 decibel. Okay, likewise if you are transmitting in the vice versa side, means that if you are transmitting the 10 decibel signal at the port 2, you will have the same 9 decibel signal in the port 1. So if you are interchanging the input port and output port, the value of the output will not get varied. Those networks are called as the reciprocal network, means that Sij, that is equal to Sji. Now, let me expand the previous slide to the three-port network. So, for three-port network, the S matrix will be 3 cross 3 matrix. So, I have written the 3 cross 3 matrix for a three-port network. Commonly, for an N-port network, the S matrix will be N cross N. And as we have discussed earlier, for matched network, the diagonal elements will be 0. Means that if we are giving in the input in one particular port, in the same port we will not get any output, because of which no reflection property. When the ports are matched with each other, there will not be no reflection, so that the S11, S22 and S33 will become 0. Okay, and as per the reciprocal property, we know that the S21 is equal to 1 2. As we have discussed earlier, if we are giving input 1, if we are giving input in port 1 and we will get the output in port 2, that will be equal to when we are interchanging the input ports and output ports. That's why as we have mentioned that S21 is equal to S12 and S31 is equal to S13 and S32 is equal to S23. So this is the basic concept. And now let me enter into the next important property. Lossless property of the input network already we have discussed in the classroom. Let me recall here for deriving the S matrix of the E-plane. And if you are looking into the unitary property, the sum of product of any term in any row or column multiplied by its own complex conjugate, that will be equal to 1. Means that the row I is equal to j, means that the I represents the row number and j represents the column number. If you are taking the row 1, we have to multiply that row 1 with the column 1 of its complex conjugate matrix. Uh, if you are multiplying, so that will be equal to 1. That is unitary property. And the second one is zero property. The sum of product of each term of any one row or any column multiplied by complex conjugate of any other different row, that will be equal to 0. Means that, for example, if you are taking row 1 and we are multiplying with the column 2 or column 3, some other different columns, that sum that total sum of that particular row will be 0. That is 0 property. So based on these properties, we are going to derive the S matrix for the E-plane T. Till now, we have discussed some basics of microwave components. Now, let us enter into the topic E-plane T. So, if you look into the figure, as I said earlier, it will have the 3 ports. So, we all know that in E-plane T, the side arm electric field is parallel to the main arm. That's why it is also called as the series T. So, for example, let me consider that we are giving the input in the port 3. Once you are giving the input in port 3, we will get the output in port 1 and port 2. When the signal is passing through this junction, in this junction, uh, the signal will get bent as shown in the figure, will bend as shown in the figure. So this bend will create the phase reversal. So in the output of port 1 and port 2, we will have the signal with equal in magnitude but opposite in phase. So that whenever you are applying input in port 3, you will get the output in port 1 and port 2. But those waves will be equal in magnitude, but they will have the 180-degree phase one. So because of this, we can write this as S13 is equal to minus S23. Means that we are giving the input in third port. We are getting the output in first port as well as in second port. Both are equal in magnitude. That's why we are writing S13 is equal to S23, and this minus which is here is represents, because of this junction it is taking the phase reversal. So because of that phase reversal, we are making it minus here. Okay, and here there is no reflection in the port 3 because it is perfectly matched. So we are considering S33 as 0. So one more basic thing is, if you are considering any microwave component, basically all the ports cannot be matched perfectly. We can match any one of the ports. That's why here S33 is perfectly matched. So remaining two are not matched with each other. And another one criteria we are considering means that whenever you are giving input in the collinear arms or main arms of port 1 and port 2. So if both port 1 and port 2 signals are in same phase, means in the output port, means that in the port 3 it will be cancelled out. And when you are giving the input of different phase or opposite phase signal in the port 1 and port 2, it will get added in the port 3. So these are all the two different criteria we will apply for the E-plane T. So now let us consider the S matrix for E-plane T. As shown in the figure, it will have the 3 cross 3 matrix. The component of the S matrix are represented as S11, S12, S13, and in the second row S21, S22, S23, and in the third row S31, S32, and S33. For this particular matrix, we are applying the three conditions. One is the reciprocal property, and another one is the matched network property, and the third one is the characteristics of E-plane 3, that is S23 is equal to minus S13. All the three properties we have discussed in the previous slides. So by applying all the three properties, the S matrix of the E-plane T will become like this, which will have the values as S11, S12, S13, and S21 actually should be here, but by applying reciprocal property, it will become S12. Likewise in the upcoming elements also, S22 and minus S13. And finally in this row S13 minus S13 0. And now we are applying the lossless property to this S matrix. So as shown in the previous slide, the lossless property of the S matrix can be said that once we are multiplying our S matrix with its transpose of complex conjugate, means that we will transpose the rows and columns and we will make the complex conjugate. So only one row I am doing here, just note it down. So S11 conjugate, 2 conjugate, I am making the transport as well as making the complex. I have done the two things here. One, I have transposed the matrix rows and columns, as well as I have made the complex conjugate. So, after that, we can able to write like this. I am making this row into second column. So what is the third element? Minus S13. So if I am writing this here, I will get minus S minus S1, and I'm taking the third row and writing it as third column. So S13 conjugate minus S13 conjugate, and here 0. And I'm multiplying according to unitary property. I'm taking a row and multiplying by the same column. So I am taking row 1 and multiplying by the column 1. That will be sent to S11 S11 conjugate plus S12 S12 conjugate plus S13 S13 conjugate. That can be simplified as shown here. S11 the whole square plus S12 the whole square plus S13 the whole square, that is equal to 1. The same we are repeating for the row 2 and column 2, row 3 and column 3, and we are doing the unitary property. We are applying the unitary property here. And when we are trying to apply the zero property, we need to take any row that will be multiplied by any other column. The value of I and j should not be equal. So I am taking the third row and multiplying with the column 1. Once I am doing so you will get S13 and S11 conjugate. So third row element is S13 and first column element S11 conjugate. And plus into minus, minus S13 S12 conjugate, and 0 into anything 0, that is equal to 0. So in these two terms, if you are looking into there, S13 is common, so you can take that outside and we can write S11 conjugate minus S12 conjugate is equal to 0. Obviously, the S13 value will be equal to 0. So, when this should be equal to 0. So, I am writing S11 is equal to S12 from here. So, from here we can able to understand S11 is equal to S12. When I am multiplying the row 3 with column 3 according to unitary property, as shown in the previous slide, I will get S13 the whole square plus S13 the whole square equal to 1, which is explained in the previous slide. So two S13s. So when I am trying to simplify this one, I will get S13 is equal to 1 by root 2. And when I am multiplying row 1 and column 1, I will get, as shown in the previous slide, S11 the whole square plus S12 the whole square plus S13 the whole square equal to 1. This simplification is shown in the previous slide. For clarifications, you can check there. And also we have said that the value of S11 is equal to S12. We have proved that in the previous slide. So instead of this S12 value, here I am substituting S11. So S11 the whole square plus S11 the whole square plus the value of S13 the whole square is equal to 1 by 2, that is equal to 1. From this I am calculating the value of S11 is equal to 1 by 2. We all know that the S11 equal to S12 equal to S22. So by supplying all these values in the final S matrix, the value of S11 1 by 2, S12 also 1 by 2, S13 1 by root 2, and likewise I am substituting all the values in the final S matrix, and this is the value of the S matrix derived for E plane T. From this E plane T, we can able to understand that for any component input network, all the three elements will not be perfectly matched. Practically, we cannot able to make match of all the inputs, and it is obeying the reciprocal property and lossless property. And when coming to the application of this e-plane T, these e-plane Ts have several practical applications. So the first one is power division, and the second one uh, is combining the powers and with controlled phase and signal values, and it is also used to measure the testing and instrumentation purpose in communication systems. Um, these are all the main applications, and let me go for the conclusion. And when we are till now we have discussed about the E20. To conclude, the E20 is a fundamental three-port microwave device. It exhibits 180-degree phase difference between the outputs. It is widely used to control the signal splitting and combining.